Something happened in a physics lab that the mainstream media barely covered. A team of scientists fired a pulse of light through a specially engineered material, and it came out the other side before it went in. Not a few nanoseconds early, measurably, repeatably, undeniably early. The effect was real, the data was clean, and every physicist who looked at the results went quiet. Because if what they measured means what it appears to mean, then one of the most lockdown rules in all of science just developed a crack. We are going to show you exactly what they did, exactly what it means, and exactly why it changes the conversation around faster-than-light travel forever. That full explanation is coming at the very end of this video, and trust me, you need everything that comes before it to actually understand why it matters. So stay with us until the last 30 seconds, because that is where the real answer lives. But before we get into any of it, quick question. Where in the world are you watching this right now? Drop it in the comments. City, country, doesn't matter. I want to see just how far this is reaching. Okay, let us start from the very beginning. For over 100 years, physics had one rule that felt more like a wall than a rule. Nothing travels faster than light. Not rockets, not radio signals, not information, not anything. Light moves at roughly 300,000 kilometers every single second, and according to Einstein, that number is the absolute ceiling of the universe. You cannot bribe it, you cannot hack it, you cannot engineer your way around it. It is not a technical limitation. It is baked into the fabric of space and time themselves. Here's why that matters so deeply. The nearest star beyond our sun, Proxima Centauri, is 4.2 light-years away. That means light itself, traveling at its maximum speed, takes 4 years and 2 months to get there. Our fastest spacecraft ever launched would take about 70,000 years to make that same trip. So even if we built something 10 times faster, 100 times faster, we would still be talking about 700 years. The scale of space does not care about our ambitions, and for a long time, the physics said the same thing. The reason goes back to Einstein's special relativity, published in 1905. He showed that as any object with mass accelerates toward the speed of light, it requires more and more energy to keep accelerating. Not just a lot more, infinitely more. At exactly the speed of light, the energy required becomes infinite, and infinity is not a number you can reach. No fuel source, no matter how advanced, can supply infinite energy. The universe does not contain it. So for generations, physicists accepted the verdict. The stars are there, they are real, and they are permanently, mathematically out of reach at any meaningful human timescale. That was the consensus. And then, in 2023, a small team of researchers published a paper that made a very different claim. They were not proposing to violate Einstein. They were proposing something stranger and, in some ways, more unsettling. They were proposing that light itself, under the right conditions, does not always behave the way we thought it did.
The experiment sounds almost too simple when you describe it. Take a pulse of light, send it through a carefully engineered material, measure when it enters, measure when it exits. Compare the two timestamps. That is the whole experiment. And for most materials, the result is ordinary. Light slows down slightly when it passes through glass, through water, through most physical substances. That is why lenses work. That is why diamonds sparkle. Light bends and slows because the material interacts with it. But certain exotic materials, engineered at the quantum level, do something different. They create conditions where a specific property of the light pulse, not the light itself, but the shape of its envelope, the peak of its wave, appears to travel faster than it would in empty vacuum. The team at the University of Glasgow, working with a specially designed optical fiber system, measured exactly this effect. The peak of their light pulse emerged from the material before the equivalent peak would have emerged if the material had not been there at all. The pulse arrived early. Now, here's where it gets philosophically complicated, and this is the part that most news headlines completely get wrong. The scientists are not claiming they sent information faster than light. That distinction matters enormously. What they demonstrated is called superluminal group velocity. The shape of the pulse, the envelope that contains it, traveled faster than the standard speed of light in that medium. But the actual information, the signal, the usable content of that pulse cannot be extracted before the light itself arrives. It's like watching the peak of an ocean wave move faster than the water molecules inside it. The peak is not carrying cargo, the water molecules are, and the molecules obey the speed limit even when the peak does not. So why does this matter at all if no information traveled faster than light? Because it breaks a second assumption, the one that said light always behaves in a single predictable way, that the speed of light is one fixed thing, full stop. What this experiment shows is that the relationship between light and matter, between electromagnetic fields and physical structures, is richer and stranger than the textbook version. And when physicists start finding cracks in assumptions, historically, that is where the next breakthrough hides. Here's the truth that the experiment is actually pointing toward, and this is what we promised you at the start. The speed of light is not one number, it is two. There is the speed of light in a vacuum, the one Einstein's relativity is built around, and there is the speed of light through a medium, which has always been variable, always been tunable, and which turns out to be far more flexible than anyone previously understood. Every serious proposal for exotic faster-than-light travel, warp drives, wormholes, quantum tunneling at scale, every single one of them relies not on breaking Einstein, but on engineering the medium that light and matter move through. The Alcubierre warp drive, proposed back in 1994, does not ask a spacecraft to exceed the speed of light. It asks the fabric of space around the spacecraft to move while the ship sits still inside a bubble. The ship never locally exceeds light speed, the space does. And what the Glasgow experiment and others like it are building toward is a much deeper understanding of how electromagnetic waves interact with engineered materials at the quantum level. That understanding is the first step, not the last, toward being able to shape the medium itself. We are not close to a warp drive. Nobody credible is claiming we are. But we are, for the first time, accumulating real experimental data about what happens when you engineer the environment that light moves through. That is not science fiction. That is physics. And physics, as history has shown again and again, has a habit of turning impossible into inevitable, given enough time, enough curiosity, and enough people who refuse to accept that the wall is permanent. The stars are still waiting. The rules are still the rules, but the rules, it turns out, have more depth to them than we knew, and somewhere inside that depth is the answer. We just have not found the right question yet.